Chapter 2 is all about measurements. Chemistry is a quantitative science. It also has qualitative aspects where you, and the difference between those two is qualitative is a descriptive term like color, differences, this is larger than that, smaller than that. Quantitative information is usually a number and a unit of measure that goes with it. Okay, here we go. And when we're taking a measurement, I keep losing the, there we go. It may not let me do that. When you take a measurement, you've always got two components. You've got the number and the unit of measure. If you say, if I were to say I'm 200, what would that mean? Well, it could mean I'm 200 years old, but I probably don't look it yet. Or it could mean I have an IQ of 200. I wish. But no, if I put the units with it that are supposed to go with 200, it would be 200 pounds. Now the 200 means something. And these dimensions, which is what the unit of measure is, what dimension is it, and how much of that unit is there, can relate to various types of measurements. We can talk about measurements of mass, which is how much substance there is. The mass doesn't change no matter where you are in the universe. You still have that same mass of substance, and we have a measurement for that. Or you have a volume, right? That's 3 dimensions. I occupy this much space, or the object occupies that much space. You can measure length. You can measure time. How long does it take to get from one point to the other? Or how much time has elapsed since we started this class today? Well, 9 minutes. Or if we don't want to use minutes, maybe we use seconds. So 9 times 60 is 54, is 540 seconds. Temperature. We have units of measure for temperature. The weather units of measure are degrees Fahrenheit. We're all familiar with those, like 32, anything below 32, you're expecting freezing weather. 70, 80 degrees is comfortable in the summer. We can measure pressure. Right? If you're checking the pressure in your tires, it'll be in units of PSI, or pounds per square inch. If you're measuring pressure in the sciences, it's usually something like pascals, or atmospheres, or millimeters of mercury. Concentration tells you how much of a substance is in a certain space, in a certain volume. And if you subdivide it, then you should get the same value of concentration in that piece as you do in the other. More detail later on that. Okay. So, the system that we commonly use in the US is the English system. And everybody has sort of an intuition about what each means. Like an inch, we have a mental picture of what an inch is, what a foot is, how much is a pound, right? Well, it depends on the substance that you're measuring as to how much the pound space it occupies. Quarts and gallons, those are English system measures of volume. But in the sciences, we use the metric system. And it's been standardized, and the ruling body that controls what each unit means is the international system, the system international, which is French for international system. And there are various units that apply to both the mass and the length and the volume. But it's a decimal-based system. And a decimal-based system is superior to the English system because the English system was sort of accumulated over time. We need a new measurement for a substance, so we invent it and relate it to some other measurement. And that conversion from one to the other is arbitrary. But in the decimal system, everything is in powers of 10. So if I have, if I know what a liter volume means, right? You have 2-liter bottles of pop, or sometimes you get 1-liter bottle of pop. Well, that 1 liter, we can speak of multiples of that liter. So if we want to say, oh, I don't know, 1,000 liters, we could say a kiloliter. Or if we want to use a smaller measurement, we could say milliliter, which is 1,000th of a liter. But it's a decimal system and it's based upon powers of 10. Okay, so the system that scientists use is the metric system. And what we need is, let's see, we actually skipped over. Sorry for doing this to you, but I think I left out a slide. So what we have in the metric system, the international system, is a set of fundamental units of measure that are fixed by this ruling body, and everything else is related to those. So for mass, we have the kilogram. Okay. For length, we have the meter. For time, we have the second. Okay. Let's see. There are a number of others. I'm stopping for a minute to think if I need to introduce those others right now or not. Let's go with those 3, so we don't complicate things too much. But each of these units is fixed by the ruling body, and a kilogram is related to a cylinder of platinum iridium alloy, and it's kept in storage in a double bell jar with inert atmosphere, probably argon, in a cave in France. And it's in a cave because the temperature is very stable. So if you want to compare your kilogram to the standard kilogram, you have to go over there or send it there, and they'll compare it and tell you how much yours actually, what's the mass of your unit. You think it's a kilogram, well, maybe it's 1.0001. So if you're going to use your kilogram, you have to make that adjustment when you bring it back to your lab. The meter used to be, actually was a subdivision of the distance from the North Pole to the equator on that line passing through on the prime meridian, which is passing through a certain location in England. And they just divided it until they had a convenient length. And then that was standardized as the meter. Well, for the longest time, the meter was also a platinum iridium bar of a certain length. It was kept in isolation and protection. And you compared your length to their length. But now we have an instrument where the standard has actually been augmented to include the ability to standardize your meter without going back to that cave in France. And you use an instrument, which is pretty pricey actually. And it measures so many wavelengths of a laser light of a particular color. And that establishes your meter. The time of seconds is actually, it's grandfathered in. Seconds have been used for centuries. So we just needed to standardize what it meant. And you can, actually, there are various, well, what would I say, standard labs that broadcast a signal. And you can pick it up if you have the right device. And the signal is a beat of 1 second each. And if your instrument is tuned to that, it can measure that interval between the beep as exactly a second. And you can standardize your equipment against that. Okay. So with these being the fundamental units, everything else is derived. So if we don't want to derive a different size mass, we need a prefix. Of course, that begs the question, this looks like it's already got a prefix, doesn't it? The kilogram. Kilo means 1,000 times. So you would expect that the fundamental unit would be the gram, and then the kilogram would be derived. But the problem is, how big is a gram of platinum iridium? It's about like that, right? So if it becomes corroded or accidentally scratched, the error that introduces in the overall mass of that little piece is huge percentage-wise. So I decided we need something bigger. So since the gram is already grandfathered in from alchemy, we'll say we're going to use the kilogram now as the standard. And the kilogram is large enough so that if it slightly corrodes, it won't seriously affect the standard. The meter, if we want to measure the distance between here and Charleston, which is about 60 miles, which would be closer to about 90 kilometers. 90 kilometers is 1,000 times a meter. So it'd be 90,000 meters. But who talks about distance in terms of thousands of things, unless you're out in space? But on the surface of the Earth, we talk about it in terms of miles, or convert that to kilometers everywhere else in the world. So a kilo means 1,000 meters. So your unit of measure now is not this long, it's that long. So the unit of measure then allows you to use smaller numbers with your unit. Okay, so each of these prefixes is a multiplier, and they're derived from the Greek. So here they are. If we say, there's the K for kilo, the kilo means 1,000, or 10 to the third, times whatever the fundamental unit is. Mega, the big M, is 1,000,000 times. G is giga, or 1,000,000,000 times, right? Everybody knows their computers. Used to be a hard drive that would hold gigabytes was pie in the sky. They were all megabytes, and they weighed a ton. They were huge. But now we've got even beyond that. Instead of the giga, now we've got the tera, which is 10 to the 12th times. And the unit there, of course, would be byte, which is a unit of information. But the prefix still means what it means. The deci is, now we're getting into tenths. So a deci is a tenth of the fundamental unit. Centi is the hundredth. Milli is 1,000th of. Micro is a millionth of. Okay, nano is a billionth of. And I think most of the exercise garb that you may buy now has some sort of nanofiber built in. Very small particles on the order of a billionth of a meter. And then when we start talking about atomic sizes, you know, the size of an atom, various parts of an atom, we're getting down into the pico, which is a trillionth, or 10 to the minus 12th of a meter. Okay, we can also derive units by simply using these, and particularly length, right? So if we have a length and we measure the side of a square or a rectangle, we can have an area. So it'd be square meters. Or if we have a volume and we measure in meters, all three sides, we have cubic meters. Those are derived units. Okay, so now we're getting into a little bit of the discussion of fundamental units. And it's good that it's here in print. The gram is okay, now we've introduced another concept and I need to explain. The fundamental unit is the one that is standardized by the ruling body, okay? But sometimes we have a base unit, and that's what we have with the kilogram. A base unit is the one that stands alone without a prefix. So sometimes the base unit and the fundamental unit are identical. But sometimes we have derived units that serve as a base unit. Example, the liter. The liter is a unit of volume, but it's not a fundamental unit. The liter is derived from the fundamental unit of length. So if you take this and take 1/10 of it, you get a decimeter. And then if you cube the decimeter, you get a liter. Okay, so we've derived a different base unit. Okay, hold on a second. There we go. So does that confuse people? I'd be surprised if it didn't. You should be less confused the more you use them. It's just important that you understand that a base unit has no prefix. So a gram would be a base unit, but it's not the fundamental unit. The fundamental unit is the kilogram. And then we can derive units and they can serve as base units. So characteristic of a base unit is it has no prefixes. Now, while we're on the subject of mass, mass doesn't change no matter where you are in the universe. Right? On the Earth, I would be something on the order of, let's say, 200 pounds. That would be maybe 90 kilograms. So that would be my mass, 90 kilograms. And on the moon, I'd still be 90 kilograms. But if I were to measure my weight let's use English terms because we have an intuition about those. My weight on Earth would be 200 pounds. But on the moon, it would be closer to maybe 33 pounds. The weight is a measure of force. So my mass is pulled toward the Earth with a force of 200 pounds. But my mass of 90 kilograms on the moon is pulled toward the moon with a force of about 33 pounds. Okay, see the difference? Now, there's a word of warning. When you read methods, like you're going to perform a lab, you may run across the statement, weigh so many grams of this substance. What we mean is determine the mass, measure out a mass equal to that. It's sort of actually it's a misused term, but it's ingrained. So just interpret in your mind. When we say weigh something, we actually mean determine the mass. There's some instructors and some publishers who have converted the word mass, which is a noun, into a verb. And they'll say, mass the substance. So that takes some getting used to, because I'm used to thinking of mass as a noun. And when you say use mass as a verb, it just twists my head around backwards. Okay. So there's your liter, which is a base unit, but it's derived. No, it's not the fundamental unit. So that's an error. The liter is not a fundamental unit because it's not established by international convention. It's derived from units of length, right? So I need to correct that. Well, I don't have my hard copy, so hopefully I'll remember. The liter is a base unit. The fundamental unit from which the liter is derived is the meter. Right, so when we say we have a liter, then we can use, well, 1,000 cubic centimeters is, these are equivalences, right? That could be confusing. Let's see, I think we have hold on a second. Yes, okay, here we go. So here's a cube that occupies 1 liter. And it's derived from the meter as a decimeter cubed. But that's also equal to 1,000 cubic centimeters. So this is a cubic centimeter here. There's a centimeter on each side. 1, 2, there's 10 centimeters. And 10 centimeters in 1 decimeter. Right? So this length on this side is a decimeter, a tenth of a meter. And a cube with a tenth of a meter on each side is a liter. But we can also subdivide that liter into smaller units. And if we go down to a tenth of a decimeter, which is a centimeter, 1/100th of a meter, right? Then we find that 1,000 of these cubic centimeters will occupy the volume of 1 liter. So as it turns out, 1 cubic centimeter then is equal to 1 milliliter, because a milliliter is 1,000th of a liter. And that's what this is. That little cube is 1,000th of a liter. So we have an equivalence there. 1 cubic centimeter is equal to 1 milliliter. And if you're in the medical profession, most everything now in the medical profession has volumes of milliliter attached to it. Historically speaking, they used to be all cc's, cubic centimeter. Well, they're interchangeable. Cubic centimeter, milliliters equal. So that's convenient. And it's probably important so that you don't give your patient the wrong volume and kill them, make them sick. Okay. Let's see. Length, mass, volume. Okay, we have equivalences, right? If we want to convert from one unit to the other, we need to know what's the equivalence. How much of this is equivalent to the other unit of measure. If we don't know that, then we can't convert from one to the other. And these are just examples, right? 1 meter length is about 1.09 yards. Various other equivalences to a meter, like 1 meter is equal to 39.36 inches. I just happen to remember that one. So a meter is actually longer than a yard by about 3 1/3 inches. So if you have the same length that you're measuring and you use a meter stick, you get a value, a unit, a magnitude, a number. And then if you use a yardstick, are you going to have more yards or fewer yards? You should have more yards because the yard is shorter than the meter, right? So as the unit of measure gets shorter, the number that's attached to it is larger for comparing equal lengths. Okay, they're inverse proportional. Let's see, I got another, let's see who showed up. Paul's phone. I assume that's Paul Hammond. All right, that's the only Paul we have in class.
I'm at work. I just logged in.
Okay.
I work on an ambulance service. I'm about to head back to station, and then hopefully I can join and finish the lecture.
Okay, I understand. And it'll be recorded, and I'll post it as soon as possible.
All righty. I'm sorry. They asked me to stay back because I couldn't find anyone.
Right.
So I got stuck.
Do what you got to do. Yeah. Okay. So those are equivalences, and we'll talk about how to use equivalences in a few minutes. Oops. There we go. Okay. Which of these represents the largest measurement of a mass of an object? So we're talking about the size of the unit of measure. All right, so we got the gram, would be our base unit, right? It's not the fundamental, but it's a base. And a micro is what? It's actually smaller, right? 10 to the minus 6, the gram. All right, so it's too small. It's going the wrong direction. Nanogram, we're going the wrong direction. Kilogram, 1,000 grams, there we go. That would be the largest one. Okay? All right. Some numbers are what we call exact numbers. That is, in fact, this is in the wrong place. Exact and inexact numbers. Okay, I see what we're getting into. We're starting to talk about significant figures. So when you have a measurement, I'll just write any number up here. Right? And the units of measure, we're going to leave those off for now because we're just talking about the number. When you have a number like that, the understanding among scientists is that there are certain parts to that number and uncertain parts. The certain parts of a number are always the first digits down to the very last, and the last digit is the uncertain. So these are certain numbers, and this is uncertain. It's essentially a guess, but we have that convention, and if a scientist sees that you've reported a number for something, they automatically assume that the last digit is a guess. So that way they can rely on this part of the number, and this one is kind of, it drifts. That's where the error is located. Okay. Every measurement that you'll ever make has an error. You may not know what it is, but believe me, there's error there. One way of finding error is to make the same measurement multiple times. And you'll see that that it'll be different. Even better, if you have 3, 4, 5, 6, 10 people make the same measurement, then the error will really pop out. Okay, so let me go to the next slide and see. Yeah, every measurement has a degree of uncertainty. whenever you make a measurement, it's uncertain. So we have the certain digits and we have the uncertain digit at the end. Now, how do we know when we're making a measurement which ones are certain and which ones are uncertain? Well, your measuring device is calibrated to with markings, so to speak, particularly if you have a length or a volume, you'll have markings. So let's use volume as an example. Say you have a graduated cylinder, and it's got markings here, right, for different volumes. I'm not even going to say what the volumes are. And then you might have subdivisions like that. Those are markings. And we fill it up with a liquid, and say the liquid is aqueous, so it's going to have a meniscus like that. Okay? Well, the certain numbers are the ones that you can attach to the nearest line on your device. Okay? The last one, the uncertain one, is the guess. For instance, if this meniscus falls between, like that, between the lines, then the certain digits are going to be associated with the lines, and the uncertain digit is going to be a guess between the lines. Okay? Hopefully I've got an example in here we can use. Here we go. So we got two devices here measuring the same object, and I need to make that point right now. If I haven't already said, nature just does what it does. It exists in length, volume, mass, whatever, time. We invent these units of measure to wrap our brains around the natural world. Nature could care less what we're using. So if you have this length, it's just that length in the natural world. It's what we call it is where the error is introduced. So in this case, we have a measuring device that's marked off in centimeters, right? So we say we've got a 3 here and a 4 here, so it's between 3 and 4, right? And then the last one is the uncertain. We're making a guess. We think it's about 0.7, right? Because between 3 and 4 are, for instance, maybe tenths. That's about as good as my eyes can work. So 3.7 here would be first certain and the last uncertain. But if we used a different device that was calibrated with tenths of a centimeter, we could say, okay, there's 3, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, all right? It's not 0.8, it's 0.7, then something in between 0.7 and 0.8. And we think that maybe that last uncertain guess is 4/10 of the distance between the two, which makes it 4/100 for the unit of measure. So 3.74 would be the value for the object using this device. Now, which gives you a better measurement? Well, of course, the one on the right, because it has more certain digits in it. Okay. Now, that being said, and recognizing that uncertainty is a given, we need a way to account for the digits in a number that we can keep during a calculation. Like we multiply two numbers together and they have the different uncertainty for each one, then how many digits can we keep in our answer, right? We need to know that, because nearly every measurement that you make is going to enter into some sort of calculation. So we start off by identifying the significant figures, we call them, the digits, the significant figures in a number. And we keep that up here for later calculation. So first we need to identify by the rules which are significant. All right. Rule number 1, all non-zero digits in a number are significant. So this number has 4 significant figures. Right? 4 sig figs. Okay. Next rule has to do with zeros. Where are the zeros located? That's important. So for zeros, any leading zeros, right? We normally wouldn't do that, right? Put zeros out here when you've got non-zeros there. But if you have a decimal like we had, like this, there we go. That still only has 4 significant figures because that leading zero doesn't count. Okay, that brings up another pet peeve of mine. Whenever you write a number, if it's a decimal fraction like this, you better have a 0 out here. I don't tolerate orphan decimals. Right? Even if you learned it in grade school and high school that you could write it that way, not in college. You always write a 0 out here to bracket that decimal. It's too easy in a narrative, if you put a number in a sentence, to mistake that for a period and not a decimal. And that would be tragic, scientifically speaking. Okay, what if we have like this? Now we've got another 0 leading. You still only have 4 significant figures in that number. All right, now, where else can our 0 go? We could put, instead of a 6, put a 0 there. 3, 4, 0, 2. How many significant figures there? There are only 3. No, there are still 4. 4 significant figures. Why? Because bracketed zeros by non-zero numbers are significant. It's important that that 0 be there. If it's not there, then you don't have 3,402, you have 342. So that 0 is so important to the meaning of the number, it's counted significant. And even if you have a decimal in there, if it's bracketed on either side by non-zero numbers, then it is significant. And this example, 16.07, has 4 significant figures. The other significant figure problem is zeros to the right. So let's go back and say, go back to our original number. And let's say, right, we've got another 0 out here past the decimal. There are 5 significant figures in this number. Because of that decimal, that 0 is significant. Okay? Now, what if you have a trailing 0 and no decimal? Then that 0 is not significant. Our example there is 150. So let's say we have, let's do this. So 34,620 is our number. We only have 4 significant figures. But if we meant to say that that 0 was significant, we put a decimal there. Now they're all significant. Okay? So those are the rules for significant figures with one addition. Excuse me. Where are we? No. Oh, we already passed it. Exact numbers. Exact numbers have infinite significant figures. Counting numbers, like I have 9 pencils. That is all the significant figures you need. So in a calculation, you can basically ignore the significant figures for exact numbers. Another type of exact number is conversion factors. That's starting to fade on me here. Conversion factors are usually ratios, like 12 inches per 1 foot. Okay, that's an exact number. If you use that in a calculation, then you don't have to be concerned with how many significant figures are in that number. All right. So how do we round? Well, there are a number of ways of rounding, but we're going to keep it simple. We're going to say, like we learned in grade school, if the number is less than 5, then in this example here, we want to round to this position right here. You look to the right, to the very right-hand number, and say, is it 5 or greater? No, it's not. So you don't change the 2. You just drop these off, and that's your answer. With this one, where we want to round off to 3, say our answer says you can only keep 3 significant figures. So we got to round it off right here. And we look to the right, just one step to the right. It's greater than 5 or 5 or greater. We round it up. So 5.01 would be our answer. Don't make the mistake of saying, well, let's see, if I'm going to round for this one, I've got to say 7, this makes that 7, this makes this 6, this makes this 5, it makes that 3. It doesn't work that way. You look just one step to the right. That's where you get the information you need to round. Okay, so now what do we do with significant figures when we're actually operating? Multiply, divide, add, subtract. Well, we have 2 sets of rules. One for multiply, divide is the simple rule. When you multiply and divide 2 numbers, or a series of numbers actually, you look for the least number of significant figures, then you take the answer that your calculator gave you, and you round down to those number of significant figures. So this number times that number gives you this in your calculator, and you say, look back, okay, that is 4 significant figures. This one has 3, so our answer can only have 3, so we round. 1 to the right says we don't change it. 15.5 is the answer. Okay, as you may have already guessed, the other set of rules is for add, subtract. Right? So for addition, subtraction, you line up the decimal before you do the operation. So in this case, we've got this number here, and we line up the decimal with this number. We add them together, and this is the intermediate step. We got these values, and then you round to the least number of digits, the least number of decimal places. Right? So let's see, do I give another example over here? Yeah, try this one. 9,333. Then we're going to add 1,400. Where's the decimals? The decimals are understood right there and right there. But these 2 zeros don't count because there's no explicit decimal. There's only an implied decimal. Right? That's important. With an explicit decimal, then we can keep everything. But with no decimal, we have to chop it off right here. Right? So the uncertain digit is at this position. That means we can't go any farther than that place. Right? So that means we have to round it to, and we don't throw away the places in here. We just substitute zeros, right? If we throw away these places, it's no longer 10,000, it's 100, right? So we can't throw away the placeholders. Got to keep the zeros, but we don't put a decimal in there. That means they're not significant. And it's all based upon where's the uncertain digit, right? The uncertain digit here is there, and here is there. It's to the left, means it's the higher uncertainty, which limits the answer. Sorry about that. That's some nosy cats messing around with my stuff. Okay, is that kosher for everybody? All right, we'll go to the next slide. Now, here's an example. We've got an addition problem, right? Because what we're going to do, we're going to add the volume of this in this container to the volume of that container. Well, intuitively, you should suspect that the accuracy, how close you can get to reality, is limited by the least accurate device, which is this one on the left. It's only good to 0.2 of a milliliter, whereas this one is good to 0.02 of a milliliter for each of these marks. Right? So if we call a number for this one, say we're going up 1, 2, 2.2, 2.4, 2.6, 2.8, and then 2.8. The last one's a guess, 2.80. And this one is 0.28. Guess the last one, 0. Okay. Now we add it together. All right. So where's the uncertain digit that limits the number that you can keep? Right here. Right there. So we throw that one out and we keep this one. Now I hope the slide says that because some of my slides are ancient and haven't been modified to keep up. Okay, so it does say 3.08 is the value that you can report legally. And of course the one on the left limits the number of digits that you can keep. Okay, here's another, this is what I said about exact numbers, right? Exact numbers have infinite significant figures in a calculation. Okay, a calculator gives you this answer when you multiply these two together. So which one of these is legal? Which one can we keep? Well, we look, this multiply divide rule. So this one has 4 significant digits. This one has 3. So we can keep 3 here. So we got to go 1, 2, 3. 7 is greater than 5. This becomes 3, 8.83. So there's your answer. Now, we're going to introduce another topic. Very often in the sciences, we make measurements or we produce calculations that have numbers that are extremely large. But rather than, we could change the units of measure, of course. You can do that to make the number more manageable. But if we're trying to compare a series of numbers, some are very small and some are very large, then we have to keep the same unit of measure for each one. So that means we need a way to express the number in a way that's more manageable. And that's where the metric system excels, because it's a decimal system, powers of 10. So we use that powers of 10 to reduce our number if it's large, or increase it if it's small, in terms of exponential notation first, and then a subset, which is scientific notation. So let's take an example. Let's say we have a number that's like that. 7.5 million. And notice you've only got two significant figures, right? Because zero's here, but no decimal. Right? So how would we express that in exponential notation? Exponential notation only requires that you have a power of 10, something here, and then your coefficient. So if the understood decimal is here, suppose we move it 3 to the left. 1, that's tens, hundreds, thousands. 10 to the third is thousands. So now we have a decimal here, but it's still understood. It's not explicit. So we would say 7500. And that still preserves two significant figures and leaves these out. That's exponential notation. All you need is an exponent of 10. Scientific notation says that this coefficient has to be between 1 and 10. So now we've got to move it 3 more places, which means we add 3 to this one. Now we have our explicit decimal here. And we've still only got 2 significant figures. So that's the difference between exponential and scientific. Scientific is a subset of exponential, and it requires that this number is between 1 and 10. If you end up with a number here that's equal to 10, what do? You change it to 1 and store that 10 over here. So you increase that one by 1, and this becomes 1 instead of 10. What if we have this one? That's too many zeros. All right. There we go. We want to write that in scientific notation. When you move the decimal to the right, the power of 10 becomes negative, right? Because this is a very small number. So the power of 10 has to be a very small number, which means negative exponents. So 1, 2, 3, 4, 5, 6. 10 to the minus 6. 7.5. Okay? Now it's important that we are able to go backwards and forwards, right? So if you move to the right to make this number, you move to the left when you take that number and go backwards. So you just move this one 6 places for your decimal place and fill in the difference with zeros. Go backwards and forwards between scientific and standard notation. Okay, so here are the rules. One of the advantages of scientific notation is if you follow the rules, you automatically get the number of significant figures. Now this one is a mistake. I can see it right now. Right here, 300, 3.00. We don't have a decimal point right there. So that's wrong. It should be 3 times 10 squared. Right? That's another error. This one looks okay. We've gone 1, 2, 3 places to the right. All of these are keepers. 4.890. We moved it 3 to the right, 10 to the minus 3. Oh, I did see that one before. What's wrong with this picture, right? Doesn't follow the rules is what's wrong. Okay, suppose we're going to multiply or divide numbers that are in scientific notation. So let's say we're going to, let's divide this one by 2 times 10 to the third power. Okay, what do you do with a number like that? If you're going to do it longhand on paper, you would take this and divide it into that. That would be your intermediate exponent, which would be 3.75. And let's just say, for simplicity's sake, so I can keep every digit, let's say that and this. Right. So now we have 3 significant figures here and 3 there, so I can keep all 3 there. Then you need to do something with these exponents. So when you're working with exponents of 10, eventually you've got to get everything into the numerator, right? Because this number sitting by itself is understood to be divided by 1, right? That's math. So this has got to go up here. So what happens when you move that up here? It becomes negative. And then when you add the negatives together, you get 10 to the minus 9. Another way of saying that is the exponent of 10 in the denominator is subtracted from the exponent in the numerator. Right? So it'd be minus 6 minus 3. If they were both in the numerator, then you would multiply them together. These two would multiply, and these two would be added. So that would be minus 6 plus 3 would be minus 3 if we were multiplying them. Those are the rules. Now, of course, with your calculator, you should be able to input exponential numbers. You have to learn how to do that. So go back to your user's manual and figure out how to input scientific notation into your calculator. You may also need to set it up so the display will spit out the answer in scientific notation. That way you won't lose information, because the calculator display is only that long, you know. And if your number is extremely small, your answer is extremely small, the non-zero digits might be out here somewhere off scale. You'll never see them. So it's important to have your output on your calculator in scientific notation. That way you always get this part of the answer. And each calculator is different. Well, each manufacturer is different. Sometimes each calculator is different. Like if you have a Hewlett-Packard, you may have different instructions on how to set these things up, whereas a Texas Instrument might be a different set of keys that you have to. So you got to go back to your user's manual and figure that out. So if we convert this number to scientific, that should not significant, scientific notation. My goodness, I didn't realize there were so many errors. Scientific notation with 4 significant figures, right? So let's say we get this, but we need to convert it to 4 significant figures. So how many of these do we keep, right? If we're going to go to the left, we're going to go 1, 2, 3, 4, 5. So that's plus 5 powers of 10. All of them have that. Okay, so we're going to concentrate on the coefficient. So 4 significant figures, 1, 2, 3, 4. 1 to the right is greater than 5, so this becomes a 2. 6.302. There it is. Conversion factors. Okay. I may have said it before, but I'll say it again. If we run out of time, I'm just going to keep talking and finish the recording. If you have to go, that's fine, because you're only obligated for 2 hours in this class, in the lecture part of the class. Okay, conversion factors. If we want to convert something to something else, we need a conversion factor. We need something to convert this unit to our target unit. how do conversion factors work? All conversion factors are based upon equivalence. Something is equivalent to something else. This unit of measure with those magnitude value, the number, is equal to 1 inch. So in nature says, all right, it's this long. Like, call it what you want to. It's that long. All right. English system says it's 1 inch. Metric system says it's 2.54 centimeters. It's the same length, but we're using different measures. Okay. So you got to have an equivalence before you can create a conversion factor. So let's say we have a, excuse me. Let's say we have something that's, I don't know, centimeters, 2,540 centimeters. We want to convert that to inches. This is the best way to do it. This is what you have, and this is what you want. So now, this has to be in the numerator. Otherwise, it's not going to be there when you get to the end. But this one has to be in the denominator because, remember, that's in the numerator. We need this one to cancel that one. In the sciences, when you do mathematical manipulations, you don't just add, subtract, divide, multiply, and power numbers. You also add, subtract, multiply, divide, power units of measure. So that unit cancels that unit because they're exactly equal. Centimeter, centimeter. And leaves the inches. Now we need something in here to make the equivalence. And that conversion says we've got 2.54. Okay, now why does that work? It works because we have this equivalence, 1 inch equals 2.54 centimeters. If we divide both sides by 2.54, then that's allowed in mathematics. Divide both sides of an equation by the same number. And the equivalence remains. Then what do you get from that? Well, look, those two cancel. So what does that mean? This divided by itself is 1, isn't it? Right? And another fact in mathematics is you can multiply or divide numbers by 1 all day long. Right? That's 1. That's permitted. I can multiply this by 1, but it won't get me where I'm going. So I need something that's equal to 1. And in that case, it's 1 inch divided by 2.54 centimeters. So that substitutes in for 1. Now it gives me what I want. All right, so this problem uses 100 centimeters. I used this one. So what we have here is actually 100. So we can keep 4 inches. Right, because this is an exact number. It has no bearing on the significant figures that we can keep. This one is the one that determines. All conversion factors are exact numbers. Okay. Okay, and now, because that ratio is equal to 1, if we flip it upside down, put the inches on the bottom and centimeters on the top, it's still equal to 1, isn't it? Right? Because if it's equal to 1 this way, it's got to be equal to 1 the other way. So it just depends on which one do you need on top and which on bottom. If this were inches, then we put inches on the bottom and centimeters on the top. And that would give us centimeters converted from inches. All right. Here are some other equivalences that can be used to make conversion factors. 1 pound is 454 grams. 1 kilogram is 2.2 pounds. 1 ounce equals 28.3 grams. Another one you can get from the grocery store. You buy a bottle of milk that's a gallon. 1 gallon of milk is equal to 3.8 liters. Just look on the label. Most of my students never look at labels. They just buy stuff. I always read labels. And here's reinforcing what I said earlier. 1 milliliter is equal to 1 cubic centimeter. And in the medical profession, you might see it marked as 1 cc. cc is easier to print on machine print on things way back before we were able to print with exponents. So that's why medical used cc rather than cubic centimeters. Okay, how would we convert 4 inches to centimeters? Well, you need inches on the top, right? Centimeters on the bottom. So here we go. Easy test-taking technique. Wait a minute, we're going to convert inches to centimeters. We need inches on the bottom, excuse me. If we're going from inches to centimeters, we need to cancel inches. So inches has to be on the bottom. It's one of these. We just need, what's the conversion? If we're going to centimeters, we need this one right here. 2.54 centimeters is 1 inch. Okay, so these are just steps for using what we've been doing with conversion factors is dimensional analysis. The dimensions are these units of measure. And if you watch and you're careful with your dimensions and you learn how to cancel them, how to use conversion factors, that's dimensional analysis. And so many problems in chemistry are solvable with just that method. It's almost as if you don't even need to know chemistry. If you're just converting units of measure, and some chemical problems require as a subset of actions the dimensional analysis. And I'll show you those once we get to them. Okay, so let's see, how much time have I got? Still good. So if a golfer has to putt a ball 6 feet, how many inches does this represent? The dimensional analysis says, where do you start from? And where do you end up? That tells you the conversion factor you need. You got to get rid of feet and leave inches. So now you need an equivalence. How many inches in a foot? 12. That's the thinking part. That's the dimensional analysis. The rest is just number crunching. If you do the thinking right, and then you don't crunch the numbers wrong, you'll get the right answer. So how many inches is that? This is about 7. So 7 times that is around 80, something in the neighborhood of 80. I'm just estimating without using a calculator. So, oh, it didn't tell us. All right, so we got to do the calculation. 6.8 times 12. 81.6 is what my calculator says. How many of those can we keep? Well, this is the deciding one. It's only 2 significant figures. So we say 1, 2, that's greater than 5. There's your answer, 82. Oh, I see we had multiple slides, sorry. But this slide did skip the part where you get the rounding, right? Keep the significant figures. My calculators don't know significant figures. They just spit out the most accurate number they can come up with, as many decimal places as they're allowed. And then we have to reason the numbers that we can keep. All right, we're going to do this one. This is an example of what I call a chained conversion. Suppose you don't have a single conversion factor to go from where you are to where you want to be. Never fear, you can chain your conversion factors together because they're all multipliers and dividers. So if we have 4.5 pounds, and we want to end up with grams, okay, what we need to do is say, all right, sometimes it's easier to work backwards. What conversion factors do we have? 1 kilogram equals 1,000 grams. All right, if I want grams, kilograms, then I use that conversion factor, 1,000 grams per kilogram. So that gives me grams, but now I got to cancel kilograms. So we're working backwards. Kilograms is on top now because that's on the bottom. And then pounds is on the bottom, so we can cancel this one. All right, so now we need a relationship there, and it's 2.2046. 2.2046 pounds per kilogram. So analyze your dimensions. Did we cancel the ones we don't want? Numerator, denominator, numerator, denominator, numerator, answer. So now we chain them together. We say that times that times that, divided by that gives you your answer. Okay? And the answer here on the slide is in scientific notation. So whatever answer you get, you keep 3 significant figures and convert it to scientific notation. Say we're going from New York to Chicago, and you need to know how much money to take, right? How are you going to get there? Well, if you drive your car, you're going to have to buy gas. Right? So how do you convert where you're going into dollars in your pocket so you can be sure and get there and come back? Maybe drive around a little bit while you're there. So let's say we're going one way, and then we'll worry about the rest of it later. Well, you need to know the distance between New York and Chicago. Right? So the distance is about 3,200 miles. Oh, wait a minute. That's wrong. My goodness. It's New York to Los Angeles, not Chicago. Okay, I said 3,200 miles. Chicago's not that far from New York. You'd be lucky if it's 1,000 miles, right? So we're going to Los Angeles, actually. Maybe by way of Chicago. So 3,200 miles is where you start. And you want to end up with money in your pocket that you reserve for nothing else but gas. Well, we've got to go from miles to dollars, but there's no conversion factor that's exactly that, right? Because every car is different. And what's different about each car? Mileage, miles per gallon. Now, why did I put one on top and one on the bottom? Because miles has to cancel and leave us with gallons, right? So let's say, just for argument's sake, you go 25 miles in 1 gallon. So now we're down to gallons. Now we need to know what's the gallon of gas going to cost on the way. So that's kind of an estimate. You say, well, it may have cost $2.75 at one time. But there you've got your chained conversion. Oh, by the way, brace yourself. price of gas is going up. There's no avoiding it because we've got a Democrat in charge. We got Democrats in both houses of Congress, Democrat in the White House. Trust me, the cost of living is going up. Okay. So which of the following is a feature of dimensional analysis? Units do not have to be considered. Wrong. Units must be considered because they can be multiplied, divided, and canceled. That's true. Units can only be divided. False. Units cannot be. Okay, B is the only answer that works there. All right. I heard a ding. Let me see. Did I lose somebody? No, we still got 10. Oh, maybe Paul's back. Okay. So what I just showed you with that previous problem and mileage, cost of traveling, is critical thinking. In other words, you break a problem down and you say, what's the question? Where am I headed? What do I need for the answer? And fill in the space in between. You need to be able to look, you need to recognize, what do I need to answer the question? Sometimes it's given in the problem. Sometimes you got to go look for it, right? So you may have to have memorized formulas. You may have to have access to a periodic table. That'll come later to get the information you need to answer the question. All right, so let's use, this is our example for problem solving using an equation. So we're going to define what is density. Density of an object is its mass divided by the volume that it occupies. For solids, that'll be grams per cubic centimeter. For liquids, grams per milliliter, which fortunately, the numbers would be equal, right? Grams equal grams. Cubic centimeters the same as milliliters. We already said that. So these two versions of density will be equivalent numerically. Now for gases, gases are so thin, you need a lot more volume to have a measurable mass, right? So usually gases are reported in grams per liter. But that formula is like any mathematical expression. In this case, we've got 3 unknowns. If you fill in values for 2 of them, you can solve for the 3rd. And that's always true with a mathematical expression. If you've only got 1 unknown, you can solve for it. So here's an example. Say we have a mineral that's a mass of 17.8 grams and it occupies 2.35 cubic centimeters. What's the density? You just plug in the numbers, right? There you go. And there you have your answer. Now, let me call your attention to the difference between capacity and intensity. It's helpful to recognize the difference in the data that you collect or the calculations that you produce. If the unit of measure and the number associated with it is a capacity factor, it does matter how much of the substance you have. Like the mass of the substance will increase the more of it I have. That's capacity. Intensity is more like a ratio. In other words, the intensity value, like density, if I have this much silver or 1 silver coin, it has a density of 10.5 grams per cubic centimeter. If I have a whole stack of silver coins, the density is still 10.5 grams per centimeter. The difference between intensity and capacity. Most of the time, intensity factors will be ratios, like this. But there's one example where intensity is a single unit of measure, and that's temperature. The temperature of that bowl of soup will be the same no matter where you measure it. You know, if it's evenly stirred and distributed, the temperature will be, well, I don't know, 100 degrees Fahrenheit. Now it has to be more than that. Maybe 120 degrees Fahrenheit. In this section, same in that section. That's an intensity factor. All right, this is a case where we know the density and we know the volume. So we got this one and we got this one. Solve for the mass. You can plug in the numbers and then solve, right, using the mathematical manipulations, or you can solve it first. Then plug in your numbers. Get the unknown on one side, then plug in the numbers and solve it. Either way works. Okay? So there's the definition of density, mass divided by volume. Temperature. We have 3 temperature scales that are commonly used. Fahrenheit is used in everyday life and weather. Celsius is the scale for all sciences, the worldwide. And Kelvin is a conversion of Celsius. So once we define Fahrenheit and Celsius, the conversion to Kelvin is simple. So let's look at it. Fahrenheit came first in the early 18th century. And it was developed by a person who was interested in the life sciences. He wanted a scale that was amenable to temperatures of living systems. So he said, all right, what's the coldest temperature I can get? Right. Saturated salt water and ice. So that was his 0 mark. And by he, I mean Fahrenheit. The guy's name is Fahrenheit. And 100 was what he assumed to be the temperature of a living system. Right? So if he stuck the thermometer in his mouth, he might say, that's 100. Well, that's kind of iffy, because if he was running a fever that day, it would be more than 100. Or if he was hypothermic, it would be less than 100. But be that as it may, since then it's been standardized as 0 to 100. And then you subdivide it. And each one of those subdivisions from 0 to 100 you make is 1 unit of Fahrenheit. Same thing for Celsius. 0 to 100, only the 0 and the 100 marks are different. 0 in Celsius is freezing point of water, pure water. Boiling point is 100. So the Celsius was developing his temperature scale for the physical sciences. And you have 0 to 100 is 100 divisions. And then Kelvin is just a conversion of Celsius where you shift the 0 point. The 0 point for Kelvin is not the freezing point of water, it's absolute 0. You can't go any colder. So Fahrenheit and Celsius can have negative values, but Kelvin cannot. It cannot go below 0. In fact, we haven't actually gotten to 0. It's a theoretical baseline. And this is what they look like together. Right? So you notice that for Celsius and Kelvin, you've got a difference of 273. So if you say Celsius plus 273 gives you Kelvin. So we would say Kelvin temperature equals degrees Celsius plus 273. And notice Kelvin doesn't have a degree mark. It's just K. So now how do you go between Celsius and Fahrenheit? Well, there's a formula for it. Notice there are two things that have to be corrected here. One is the 0 point, right? 0 for Celsius is actually 32 Fahrenheit. So we've got to make a 32-degree correction for 0. Then we have to correct for the size of the degree. The size of the degree for Celsius is larger than Fahrenheit. So when you convert from Celsius to Fahrenheit, it's going to take more degrees to fill in that space. So here's what it looks like. Fahrenheit equals, degrees Fahrenheit equals 9/5 degrees Celsius plus 32. Okay? Now your book might say 9/5 is 1.8. That's the same number. That fraction versus 1.8. If you know that formula and you fill one of them in, you can solve for the other one. So this is the only one I ever memorized because I knew I could always manipulate and solve for the other one if I wanted. Okay, so there they are. This is the one I memorized right here. This is simple. Just add 273 to Celsius. If you have Kelvin, just subtract 273 and you get Celsius. If you want to know how this formula was derived, just go to this link right here and it'll show you. I'm not going to take any time to tell you right now. Another interesting question is, we know that if we plot Celsius and Fahrenheit, we get a different slope lines. So that means somewhere they're going to meet. That means at some point, Celsius number equals Fahrenheit number. And to know what that temperature is, we just take the formula and we say, all right, if this is going to be equal to that, we just substitute an unknown x in for it. Now we've got an equation in one unknown, we solve for it. Turns out that minus 40 degrees Fahrenheit is the same as minus 40 degrees Celsius. Okay? Let's see. I better keep moving so I don't run out of time. Most thermometers are accurate to 1 degree. So if you read 10 degrees C or 10 degrees F, that's only 2 significant figures. If you get up in the range of hundreds, then you get 3 significant figures. But the uncertainty is in the, actually, if I follow my rules, if you have markings on the thermometer for 1 degrees, then you should be able to estimate in between, even if you just estimate half a degree. In which case, I could say maybe if it was halfway between 10 and 11, I could say 10.5. And then the 0.5 would be the uncertain one. There are thermometers that are calibrated in much finer detail, and they're about as long as your arm. So, but now we have electronic thermometers that will read out a digital value, and they operate on a different principle, usually a thermocouple, which varies its resistance based on the temperature. And the electronics inside the thermometer interpret that change as a temperature. Okay, so this one converts from Celsius to K. Let's see, what is this one? An individual has 300 milligrams of trazodone each evening before bedtime for 1 year. How many pounds of trazodone he or she consumed? 450 grams in a pound. This is going to require multi-step conversion. And let me take a look. I think I have another concept question. I may not be able to get to both of them. So let's do this one. And that should finish out the day. So where are you starting? I like to put the information up on the board or on my paper separate from the word problem. Because if there's one thing that's constant about word problems, is that they are designed to confuse. And the reason they're designed to confuse is so that a student that's reading the problem, if they don't know what they're doing, they can't get the problem right. They can't get the answer right. So I extract the information from the problem. Okay, we've got 300 milligram trazodone each evening for that. So that's per day. 300 milligrams per day. All right. This is shaping up to be a dimensional analysis problem. And we want the answer in pounds. Okay. So how do we get from here to here? Well, this is only one unit of measure. So somewhere in here, we've got to cancel out the time to get pounds, or we could do pounds per year, right? That would be valid. So here, what we've got is 2 units of measure that have to be converted. When that happens, convert 1 unit at a time. Your conversion factors just operate on 1. Right? So we want to go pounds. So we know that 454 grams is in a pound, but that's not grams. So we need grams here. 10 to the third, there. Now we can go grams to pounds. Right? Milligrams cancel, grams cancel, 454 grams per pound. Now we got pounds. That part's done. Now we need to do the time. So I'm going to wrap around, right? Come over here. So how many days in a year? 365? Actually, it's 365.4. But we didn't take trazodone on 1/4 of a day, right? So 365 is one we'll use. There you go. Oh, that's wrong, isn't it? Oh, no, that's right. Because I moved it down here, it kind of threw off my vision. This is in the numerator, that's in the denominator. So they do cancel. And this is in the denominator here and here. We're good. So now we just need to do the math. 300 times 1 times 1 times 365. Divided by 1, divided by 1,000, divided by 454. There's your answer. And if you do that math, you should get 0.241. And we're limited to 3 significant figures because I put a decimal there. They didn't put a decimal here, which there should be. Right? Otherwise, we're limited, and we could only say 0.2 pounds rather than 0.241. But assume there's a 0 there because I put it up here on the board. And that should be the answer. Okay? All right, we got a few minutes. We can do this one. Usually the concept questions on my slides come at the very end, so I think we're close to the end. Let me see. Let me get my... yeah, okay. I just want to be sure I'm still on camera there. Whenever I go to click the slides, the pictures disappear. The participants disappear. Okay, so if you're given a pound of feathers and a pound of lead, the density of each would be what? The same or different, right? Look at your answers. The same, different, different. Density is a capacity factor. It's characteristic of the substance, and it changes if the amount of substance per volume is different, which means that it is different, right? The density of feathers is less than the density of lead. So it's either C or D. Test-taking technique, process of elimination, right? we can forget about A and B because they say the same. Neither one of those can be right. So different, one of these. The density of each would be different because why? Well, C says the mass of lead is greater than the mass of feathers. Well, look, you're given a pound of feathers and a pound of lead, so the mass is not different, right? We're on the surface of the earth, so the weight is proportional to the mass, right? So if we're given a pound of each, they have the same mass. So that can't be it because they have the same mass. It's not difference in mass, it's difference in volume. A pound of feathers would be like fill this room. A pound of lead you could hold in your hand. So D would have to be the answer. Critical thinking, test-taking technique, process of elimination. What's the information you're given? What is the question? The question is, what's in these blanks that fits with the rest of the statement? Okay, I think that's it. Yeah, so I can stop the share and see if there are any questions